All right, so in this video, we're going to go over frames and how to solve problems that involve frames. So essentially, a frame is just a pin-connected structure with multiple forces on them. And in terms of identifying them on an exam where they won't necessarily tell you, hey, this is a pin problem, frames are the ones that don't look like bridges, right? Because bridges are pin connected structures with multiple forces on them, right? So bridges and frames are not the same, right? So yeah, and then another thing that's important that I forgot to write is that it will always ask you for pin reactions. So that's important because once we get into internal forces, it'll start asking you for forces inside of members, but here it's asking you for pin reactions. Essentially the premise is exactly finding those pin reactions. And you do that by, once you see the problem, you take the structure apart and then you expose those reactions. And then essentially you just solve with equilibrium equations. Now the problem is you only have 3 equations at the most, right? And because of that, you have to have 3 unknowns or fewer to solve one section of the body. So that's kind of where frame structures become a little difficult to evaluate because it becomes a game of hopping back and forth between one member and another to solve the problem. And we'll get into that in a second. Super quickly, I just wanted to look at one of the more simple explanations just to kind of like go over a few things that I might not have hit up at the top. This was a problem from frames 1. So yeah, it's definitely a simpler problem. Definitely will be more complicated on an exam, but it's good to explain the core concepts, right? So the first thing you have to do is you have to consider what the free body diagram of the entire system looks like. So here I drew it. You might not always be able to do something with it, but you draw it. And then you pull the pins where there's 2 members that are connected, right? So on this body, there's a lot of pins. There's a pin here, there's a pin here. Oh, wait, that's not a pin, that's a rocker. There's a pin there at B, there's a pin here at D. Sometimes you can have like pins as supports, but you only want to pull the ones where it's connecting 2 bodies. So the only pin that does that is at D, right? So I separate it into um, my two members, right? So basically it's separated right here. And an important thing to remember is that because pin D was the connection point, and in the original problem up here, we're looking at it as an equilibrium problem, right? So it's not moving. You have to make sure that whatever forces you're exposing at D ultimately are equal and opposite to each other, right? Because ultimately they have to cancel back out if you were to put it back together. So that's why you always have to make sure when you're drawing your unknowns at those pins, the arrows are always equal and opposite to each other if they show up on more than one body. And then you just go into evaluating how many unknowns there are, because right, if I can solve it right away, if I can solve, one member right away, that's the one I should start with, right? So here I have 5, right? I have AY, BX, BY, and DX, DY. So I have 5 unknowns on this one. Here I just have dy, dx, and cy. So I have 3 unknowns here, which means I can solve this one because I have 3 equations. So that first step, or the next step, I guess, is solving whatever you can right off the bat. So here that's solving DC because I have an appropriate number of equations to do that. So after that, by solving DC, I then have the values for the reactions dx and dy, which I can then transfer over here because I know they're equal in magnitude and opposite in direction. So I can transfer those over, and now on this side, I only have ax, bx, and by. So now I can solve this one because there's 3. So at the end of the day, I only needed to solve 2 free body diagrams because it solved itself. And I was able to solve one of them entirely before moving on to the next one. Now, it's important that in your answer, you make sure you're clarifying what body it's on, basically. So the problem is going to ask you for the pin reactions at D, but the pin reactions at D show up on 2 different drawings, right? So it shows up on this one and on this one. And if I said that what did I say? If I said dx is 50 newtons to the right, that doesn't really help me because either of these arrows could be to the right. You know what I mean? So because of that, it's important to clarify which body you're looking at. So that's why you have to include on ABD or on whatever body you're looking at. So that was nice to explain some of the core like fundamental things, but that's definitely not what you're going to see on the exam because that was pretty simple, right? So looking at a problem from frames 2, which is the more complicated frames problems, right? This one kind of considers more members, right? So here we have 1, 2, 3, 4 different components of this of this structure, right? And the first step I would do is look for any 2 force members. And remember, a 2 force member can be any shape. It just has to have nothing acting on it except the pin reactions at its ends, right? So in class, a lot of people were asking about whether AC, right, this member here, would be a 2 force member. And in this case, it's not because you have that pin at point B that's going to cause forces on it. So even though it doesn't look like there's any forces on that body or on that member, there are. So here you can only simplify it to 4 free body diagrams. And here they are. So basically, I'll walk through these really quickly, but what I wanted to walk through is the logic of how to solve these, right? So looking at the first one, I think I started with BD, right, which is this member that goes across. So I pulled a pin at B, which means I have BX and BY, right? And then E is also a pin, so I pulled that, EX and EY. And D is a pin connecting it to a pulley, so DX and DY. There's no other forces acting on BD, so that one's done. And I just put the dimensions and we're good. Looking at AC, right? A is a pin, so I put AX and AY. B is a pin that I pulled already, so I have to make sure that they're equal and opposite here to here, which they are because on BD I drew them down and to the left, and on AC I drew them up and to the right, so that's good. And then on C, I have a pin that I pulled, so that becomes CX and CY. And then moving over to CF, which is this vertical member here, C is a pin I pulled, so I have to make sure it's opposite on this one and this one. Basically, what will end up happening is I drew one of them up and to the right, one of them down and to the left. That works. E is a pin I pulled. I have to make sure it's opposite here and here. I drew up and to the right on one, down and to the left on another. Let's see what else. F was a roller, so that's something to pay attention to. This here only has a support in the Y direction. So that's FY. And let's see, what's the other thing? Oh, so this pulley here, we'll look at the pulley itself in a second, but this rope is pulling on CF. And because the rope is simply just like moved over, right? It's rolled over the pulley. It's like the same rope still. The tension's the same. So because it's loaded at 300 pounds, there's 300 pounds moving through this entire wire, which means this arrow here is 300 pounds also. The force pulling on CF. That brings us to the pulley. The pulley is pretty simple. Those are my favorite because they're so easy to actually solve. You just have the pulley itself, and then you have the force going down because obviously it's got a load on it. And then you have a force going to the left because that has a load on it. And in the middle, we pulled this pin at D. So it has to be equal and opposite to wherever else it was, which is right here. So here I drew it down and to the left, here is up and to the right, so we're good. So after you do all that, this took probably the most time. It took pretty close to like 10 minutes maybe. So this is something that I would absolutely make sure you're taking time with. But what I really wanted to go over is writing the steps of how to solve the problem, right? So obviously you have a lot of unknowns. I have 2, 4, 5 on this one. I have 2 on this one. I have 6 on this one, and I have 6 on this one. So right now, I'm struggling to actually solve this, right? Because there's a lot of unknowns. There's 19 unknowns in this problem. So it becomes kind of like a puzzle. And that's why I love these problems, because they're almost fun, basically. So what I'm going to do is I'm going to walk through the logic of how I would solve this problem, right? And then I'm going to write the steps out on the side here. And basically what I would recommend is I would recommend doing this on the exam, because you don't necessarily get a lot of time on the exam. And if time has historically been a problem for you, you can get partial credit by listing out the steps you would do here and then working through them as fast as you can. But the benefit is Dr. O'Neill will know what you were trying to do after, like, even if you weren't able to solve it initially right off the bat. So the first step I would do is start by solving this pulley, because remember, this one only had 2 unknowns, so that I can solve. So I would start by doing the sum of the forces in the y direction on pulley F, and that would get me dy. I would then do the sum of the forces in the x direction on pulley F, and that would get me dx. So now I have this one, but also this one and this one, right? And then moving on, I know I just did something to this first free body diagram BD. So let me try to see what else I can do. Well, if I take the moment about B on BD, BX will cancel, EX will cancel, BY will cancel, and DX will cancel. So I'm left with an equation with EY and DY. But I know DY, so I'm able to solve for the unknown EY. Following that same logic, I could do the sum of the moments about E on BD, and from there I can solve for BY. So EY and BY are canceled, but so that also happens over here, right? So then it becomes a game of what else can I do? So if I take, let's see, if I do on CF here, on this one, if I do the sum of the moments about C, what I can get is EX, right? Because CY and CX will cancel, EY will cancel, FY will cancel, so I'm left with EX and a number. So let's see, sum of the moments about C on CF, and that leads me to oh my gosh, I'm sorry. And that leads me to get EX. And then same logic, I can do sum of the moments about E on CF, and that will let me calculate CX. So now I have EX and CX, and then I have CX and EX. So now looking back at BD, right, I can take the sum of the forces in the X direction to find BX on BD to find BX. All right, so now I have this whole free body diagram done, and I have these two. So what I can do now is I can say, all right, on AC, I can do some of the forces in the X direction. And that'll get me AX. So now I have AX done. I can do sum of the moments about C on AC. Sum of the moments about C on AC. And that will get me AY, right? I can do sum of the moments about A on AC, and that will get me CY. So now I have those two, and now AC is done. So the only other thing I have to do, now I have CY. So then the last step is sum of the forces in the Y direction on CF, and that will get me FY. So if you look at it, this question was asking for the horizontal and vertical components of the force at C, which member ABC exerts on member CEF. So I'm looking at what this member is doing to this member, right? So I would use my answers to CX and CY on AC. So if you look, I solved for CX here and I solved for CY here. So you do normally have to do almost all of the steps. They'll end up asking you something about a question or about a value that you have to find later on in the problem, like the calculation. But if you look at here, I solved this one on CF. So say I got CX equals 10 newtons to the right, right? That would be on CF. That means that in my answer, it's asking about what's happening on ABC, right? So my answer is going to have to be this one I already found in the right, like magnet, like on the right body, right? So it's already on AC. But what I have to do to convert CX is I have to switch the sign. So that would equal to 10 newtons to the right on ABC. And then just like before, every time you write an answer, you would have to include on in your answers. But basically, if you can figure out what all of these steps are, you can absolutely figure out what your let's see, you can absolutely figure out the math part because the math is just using numbers for this. So in terms of partial credit, I would especially if you feel crunched on time, I would absolutely recommend writing this stuff out so that at least you can show that you know the mechanics part of it. I'm not going to say you're going to get a perfect score, but you'll get most of it because you know, or Dr. O'Neill will see that you know the mechanics. So that's pretty much it for frames. Other than that, we got into internal forces 1 today. So I'm going to probably start writing the notes for it. And if I get that done in a reasonable amount of time, I'll post it today as well. But internal forces is essentially the same thing, except you are looking at the internal forces inside the member itself, not inside a pin. So it's very similar conceptually.